So in this example, we have equation of the plane S, x plus 2y plus 2z equals 0. And we want to write W as a linear combination of a vector in the plane and a vector orthogonal to the plane. So in this first picture here, we have our plane S, and we have our vector W. And we have vector W as a combination of the projection of W onto the plane, so that's a vector in the plane, and an arrow vector, which is orthogonal to the plane. So based on this picture here, we have W equals the projection of W onto the plane S plus the arrow vector. But we have the equation of the plane, which means that we know the normal vector. So here's our normal vector, and as we know, normal vectors are orthogonal to the plane. So that means this arrow vector can actually be written as a projection of W onto the normal. And then we have this vector y, which is in the plane and which is also orthogonal to n. So vector y is the same as this projection here, and our projection onto the normal is the same as our arrow vector. So an equation based on this picture here would be W equals vector y plus the projection of W onto our normal vector. So let's calculate this projection value here. So the projection of W onto n equals the dot product of W dot n over the dot product of n dot n times the normal vector. And now our normal vector we can get from the equation of the plane. So we just take the coefficients from this equation. So we have 1, 2, 2. So that's our normal vector. So let's calculate these dot products. So we have W, which is 1, 2, 3, dot n, which is 1, 2, 2. And on the bottom we have n, dot n. And this is all multiplied by vector n. So to calculate the dot products, you multiply the first two terms together, plus the multiplication of the next two terms together, plus the multiplication, that would be 4, plus the multiplication of the last two terms together. And then by our normal vector. So now we have all of the pieces of this equation except for y. So let's solve for y. So here's our W and our y, which we don't know yet, and our projection, which we have figured out. So let's multiply everything by 9 to get rid of the fraction. And then we'll move everything over to the other side except for the y term. So I've just calculated this here by going 9 times 1 minus 11 times 1, and then I do that for each row. Now I'm going to divide each side by 9. So now we have our value for y, the vector y, so we can sub everything back into our original equation. So we have vector W, then we have vector y, and our projection, or our arrow vector. So this is W as a linear combination of vector y, a vector in the plane, plus the projection of W onto vector n, which is a vector orthogonal to the plane. And now to check to see if you calculated this right, what you can do is calculate the dot product of y by n, and that should equal 0. Because we know that vector y is orthogonal to 0. vector y is orthogonal to the normal vector, so their dot product should be equal to 0.